Hello everyone. Today we are going to study about the DNF block elements theory part 4. And today we are going to cover the NCERT section 4.3.7 to 4.3.11. So let's begin with our today's topic, NCERT chapter 4, DNF block elements theory part 4, NCERT section 4.3.7 to 4.3.11. This is disclaimer. So let's see today's objective. So after attending this lecture, you will be able to understand the general characteristics of D block elements and the general horizontal and the group trends in them. The topics that we are going to cover today, according to the NCERT, are the subsection 4.3.7, which is trends in the stability of higher oxidation states, 4.3.8 subsection, which is chemical reactivity and the E0 value, 4.3.9, which is magnetic properties, 4.3.10, formation of the colored ions, and 4.3.11, the formation of complex compounds. Then we will cover one example, 4.8, and an in-text question, 4.8. So let's begin. The general properties of the transition elements. So we have been studying about the general properties of the transition elements. Previously, the physical properties, variation in atomic and ionic size, ionization enthalpies, oxidation states, trends in the M2 positive to M standard electrode potentials, trends in the M3 positive to M2 positive standard electrode potentials. Now today we are going to cover the topic trends in stability of higher oxidation states, chemical reactivity and the E0 values, magnetic properties, formation of colored ions, formation of complex compounds, and later we will going to cover catalytic properties, formation of interstitial compounds, alloy formation. So let's begin with today's lecture, starting with the strengths and stability of higher oxidation states. So in this subsection 4.3.7, first we will talk about the halides of the 3D metals. The halides of 3D metals. That means the metals that covers in the 3D series or the 3D block, the halides formed by them. Okay, the halogen compounds formed by the 3D metals. Highest oxidation states. So the highest oxidation number are achieved in titanium X4. X is representing here any halide. Okay, we are calling it as tetrahalide structure, TiX4. Okay, where X is representing the halogen, and here the oxidation state of the titanium is +4, which is the highest oxidation number achieved by the titanium. Vanadium pentafluoride, where F is fluorine, V is vanadium, and vanadium is in +5 oxidation state, which is the highest oxidation state of the vanadium. Chromium F6 similarly. So let's see a table showing the formulas of halides of 3D metals. So you can see this table where the oxidation number are given, and at that particular oxidation number, the compounds, or you can say the halides formed by the 3D metals are given. So in the +6 oxidation state, only one halide is forming, that is chromium hexafluoride, right? At +5, VF5 and chromium F5. At +4, TiX4, VX41, CrX4, MnF4. Okay, that means titanium X4, vanadium X4, chromium X4, and manganese F4. Right? Now, if you see that the manganese here is existing in the tetrafluoride, MnF4. But if you remember, the oxidation state shown by the manganese was maximum, right? It was showing, the manganese was showing +2 to +7 oxidation state. But here in the halides, the manganese is forming only the halides in +4, +3, and +2 oxidation state, right? And if you compare that, chromium is showing the maximum number of the halides in the various oxidation states, right? So if you see copper is becoming only copper X2 second and copper X third. Okay, and zinc is only making halides in one oxidation state or number, that is +2. Okay, nickel is also in one oxidation number, that is +2. Okay, where the X, wherever the X is present, it is representing fluorine to iodine, and X1, like here in the iron, it is representing fluorine to bromine. X2 is representing fluorine and chlorine, and X3 is representing chlorine to iodine. Okay, so you can see X1 is here, FeX13. That means Fe can form fluorine to bromine. Fe can combine with the fluorine to the bromine halides and form trihalides or dihalides. Similarly, if you see copper, X2 second means fluorine and chlorine. That means copper can form the halide with the fluorine and the chlorine dihalide, and copper halide, cuprous halide, is formed with the chlorine to iodine molecule. Okay, and yes, TiX2 third. X third is representing chlorine to iodine. So except fluorine, uh, Ti, that is titanium, is making the halide with from the chlorine to the iodine. Okay, so this is how the formation of different halides with the halogens in the 3D metals is shown with having different oxidation number. So the halides of 3D metals, we will talk about this more now. The role of fluorine. What was the role of fluorine? Fluorine has a unique ability to stabilize the highest oxidation state. If you observe in the table, we have seen the highest oxidation states of the elements was stabilized by the fluorine. Okay, this is due to its higher lattice energy. For example, in the COF3. So higher lattice energy means the energy due to which the small size of like due to the small size of the fluorine it is having higher lattice energy. Lattice energy means the energy needed to convert the ionic solid into the gaseous ions, right? So fluorine is having higher lattice energy and higher electronegativity. Also, its high bond enthalpy terms for higher covalent compounds. For example, it is observed in vanadium pentafluoride and the chromium hexafluoride. Okay, so these are the two reasons due to which the fluorine has this ability to stabilize the higher oxidation states of the 3D metals. Now, vanadium halides. So we have seen that V in the +5 oxidation state is represented only by the V pentafluoride. Okay, not any other halide is making the halide compound with the vanadium, where vanadium is having +5 oxidation state. So other vanadium in the +5 oxidation state halides undergo hydrolysis to form the oxohalides, that is VOX3. Okay, so vanadium in the +5 oxidation state is only present in the vanadium pentafluoride, and except the fluoride uh, of the vanadium, where the vanadium is having +5 oxidation state, other vanadium halides where vanadium should have +5 oxidation states undergo the hydrolysis process to form oxohalides, that is VOX3. Now instability in the low oxidation states, showing by the fluorides. So fluorides tend to be unstable in the lower oxidation state. So the elements which are existing in the lower oxidation state, they do not form the fluorides. Okay, so fluoride, why? Because the fluoride of the 3D metal in the lower oxidation state is unstable. For example, VX2, vanadium dihalide, where X is only chlorine, bromine, and iodine, not fluorine. Similarly, copper X, where copper +1 halides are like formed, and where the fluorine is not involved. Okay, so fluorine show the instability in the lower oxidation state due to its higher lattice energy and higher electronegativity, and that is why the elements in the 3D metals in the lower oxidation state doesn't form the fluorides. Now copper halides. So all the copper plus 2 halides are known except the iodide. Okay, so copper exists in the plus 2 oxidation state. Now every halide formed in the copper plus 2 oxidation state except iodide. So copper in plus 2 oxidation state combined with every halogen except the iodine. And why? Because the reason for copper I2 instability is that copper I2 means the copper is having plus 2 oxidation state and it is copper iodide. But it doesn't, it is not known. Why? Because of its instability, and reason behind that is that copper 2 positive ions oxidizes I negative ions to I2 molecule. Okay, so when copper 2 positive reacts with the halide ion, that is iodide ion, then it oxidizes the iodide ion to the I2 that is iodine molecule. So two copper following this reaction, 2 copper 2 positive plus 4 I negative ions converts to Cu2 I2 in the solid form plus I2. So what copper 2 positive did, it oxidized the iodide ion into the iodine molecule. Okay, so that's why the Cu I2 where the copper is having plus oxidation state is unstable. Okay, copper in the plus 1 instability in aqueous solution. Now in aqueous solution, copper in the plus 1 oxidation state is unstable. Many copper in the plus 1 compounds are unstable in the aqueous solutions and they will undergo the disproportionation. Disproportionation means they will dissociate into the further ions. So like copper positive, it will going to convert into copper 2 positive plus copper. Okay, so it will disproportionate in the aqueous solution when copper is present in plus 1 oxidation state. Stability of copper 2 positive aqueous ions. So stability of copper 2 plus aqueous ions over the copper plus aqueous ions is attributed to much more negative hydration enthalpy of the copper 2 positive aqueous. Okay. So why is it so that the copper 2 positive aqueous ions are more stable compared to the copper plus 1 aqueous? Because of the more negative value of the hydration enthalpy of copper 2 positive aqueous ions. This highly negative hydration enthalpy more than compensates for the second ionization enthalpy of copper. Okay, so basically copper when need the second ionization enthalpy, it has to lose its 2 electrons, one from the 4s1 and one from the 3d10. D10 is already stable, but still the second ionization energy which it needs to remove the 1 electron from the 3d10, okay, is larger. But the highly negative hydration enthalpy compensates this second ionization enthalpy of copper, and the copper 2 positive in the aqueous solution due to the negative hydration enthalpy becomes stable compared to copper positive aqueous. Now the oxides of 3D metals. So continuing on this, highest oxidation states in the oxides. Ability of oxygen to stabilize highest oxidation state is clearly demonstrated in the oxides. If you see the oxides of transition metals or 3D metals. So here is a table 4.6 showing the oxides of 3D metals. The oxidation number is present +7 to +1, or you can say +1 to +7, right? And the group 3, group 4, group 5, group 6, group 7, group 8, group 9, group 10, and 11, and 12. The metals of transition elements are given, forming the oxides. Okay, so in the higher oxidation state, the oxygen is going to stabilize the compound. Like if you observe, the manganese existing highest oxidation state is +7, and manganese is forming Mn2O7 in the +7 oxidation state. right? And it is the stable one. Okay, so highest oxide that is stable for the manganese is Mn2O7. Now the highest oxidation number in the oxides is generally coincides with the group number. If you observe that the highest oxidation state is here for the scandium is +3, and scandium is also covering in third group. Similarly, like if you see in the manganese, manganese is coming in the +7, uh, manganese is coming in the seventh group and also showing the highest oxidation number as +7. So highest oxidation number in the oxides of the transition elements generally coincides with the group number. Okay, so why this superiority of oxygen is present? That if you compare, we have seen that manganese is forming tetrafluoride. Like that means +4 oxidation state is showing by the manganese tetrafluoride, and it is forming MnF4. But uh, manganese can exist in various oxidation state up to +7. Still, it is showing the highest uh, like stable fluoride was MnF4 in the +4 oxidation state, right? So superiority of this oxide, and if you see this oxide found by the manganese is having +7 oxidation number of manganese, right? So manganese in highest oxidation state is forming its stable oxides. Okay, so why? So the superiority of the oxygen is due to the ability to form multiple bonds to the metals by the oxygen. Okay, so if you observe the Mn2O7 like structure, the MnO-Mn bridge is present in this. Also, each manganese tetrahedrally surrounded by the oxygen molecules by like double bond. So, due to this ability of oxygen, oxygen going to stabilize the highest oxidation state of manganese, which you can clearly see in this table. This trend is observed from scandium 2032 to manganese 27. Okay, scandium 2032, manganese 2O7. If you see, like each element is having their oxides stable in their highest oxidation state, right? Now let's talk about the iron oxides which come after the manganese. So beyond the group 7, no higher oxides of iron above Fe2O3 are commonly known. Ferrets, in which the iron is having +6 oxidation state. Here iron is having uh, +4 oxidation state in this Fe2O3, right? Which is a higher oxide of Fe, which is known and which is also stable. But if we talk about ferrets, in which iron is having +6 oxidation state, having formula FeO42 negative, this can be formed in an alkaline media, but they are unstable and they readily decompose to Fe2O3 and the oxygen molecule. So Fe in the +6 is unstable, or they form the compound or the oxides which are unstable and they will decompose to oxygen and the further oxides of the or stable oxides of the iron. Oxocations. Oxocations. So oxygen can also stabilize high oxidation states through the formation of oxocation. So oxygen can also stabilize high oxidation state via the formation of oxocations. This is the another way. So for example, vanadium in +5 as VO2 positive. Okay, so vanadium which comes after, so vanadium in the +5 as VO2 positive. So it is forming a oxocation, oxygen in the cationic form. Okay, oxide in the cationic form, in which the vanadium is having +5 oxidation state, which is stable. So oxygen can also stabilize the higher oxidation state of the elements through the formation of the oxocations also. So another example is vanadium in +6 as VO2 positive. Titanium in +4 as TiO2 positive. Okay, so these formation of oxocations are forming through the oxygen, and also in this the element are existing in their higher oxidation state and also the stable Comparison with the fluorine. Now, if you compare with the fluorine, ability of the oxygen to stabilize these high oxidation state in the oxocations exceeds that of fluorine. Okay, now if you compare with the stability of fluorides that has been formed with the 3D metals, the oxide that are forming by the oxygen to stabilize the higher oxidation states by the formation of oxocations is exceeding the fluorine. Okay, so ability of oxygen to stabilize the higher oxidation state in the oxocations exceeds that of fluorine ability. Okay, now we will talk about our next subsection, which is 4.3.8, that is chemical reactivity and the E0 value, standard potential value. So chemical reactivity of transition metals. Transition metals exhibit a wide range of chemical reactivities. Many are electropositive, enough to dissolve in the mineral acids. Some are considered noble and are unaffected by the single acids. Okay, so we are talking about the reactivity which is shown by the transition metals chemically. Okay, so they exhibit a wide range of chemical reactivities. Many are electropositive enough to dissolve in the mineral acids, and some are also considered as noble. Noble means they attain the noble gas configuration and they are unaffected by any single acid. Reactivity of first series 3D metals. So, with the exception of copper, the metals of first 3D series are relatively more reactive. They are generally oxidized by 1 molar H positive, that means proton. Important note here is that actual rate at which these metals react with oxidizing agents like hydrogen ion can sometimes be slow. Okay, at some exception points, because we are studying DNF block elements, there always be an exception here. So we are saying that exception of copper, with the exception of copper in the first series of 3D metals, they are relatively more reactive because they are generally oxidized by H positive. And a thing to note here is that the actual rate at which these metals react with the oxidizing agent like H positive, the rate we are talking about, can sometimes be slow. That means maybe they are not as much reactive or the rate will be slower at some cases. Passivity example, that titanium and vanadium, for instance, are practically passive. That means unreactive to the non-oxidizing acids at the room temperature. Okay, so titanium and vanadium unreactive to the non-oxidizing acids. Why? Because of the formation of a thin stable oxide layer on the metal surface, which is going to act as barrier against the further reaction to happen. Okay, so these are the example of this important note given here. Now, standard reduction potential E0 and reactivity. Standard electrode potential E0 and reactivity. So trend in the E0 values, that is M2 positive to M. So E0 value for M2 positive to M half cell generally indicate that a decreasing tendency to form a divalent cation, that is M2 positive, across the 3D series. So the E0 value, if you observe for the M2 positive to M half cell, it is indicating that there is a decreasing tendency to form the M2 positive from M across the 3D series. This trend corresponds to increasingly less negative E0 value. If you observe in the 3D series, the E0 value become less and less negative successively. If you observe this table where the elements of the 3D series is given from scandium to the zinc with their atomic number, electronic configuration in each ionic form, standard electrode potential in the vault from M2 positive to M and M3 positive to M2 positive. Right? If you observe that they all are in negative except the copper one, and also the E0 value here is less negative. It is becoming across the series less negative. Okay, that means the tendency is decreasing to form the divalent ion from the M that is metal. Okay. If you observe this minus 1.63 decrease to minus 1.18 decrease to 0.90. Now here is a manganese is sudden increase. Okay. So expected is that from minus 0.90 it will going to decrease, but it is increasing. Why is it so? Now it can relate to the manganese half filled configuration, that is, it is going to attain in the M2 positive state. So when manganese is going to attain the D5 configuration, that is half filled stable configuration in the Mn2 positive, that means it is going to show the more negative E0 value because it wants to attain that D5 half filled stable configuration, right? So it will show the higher negative E0 value. Now the iron E0 is decreasing, then decreasing, then decreasing, then copper is having, this is exception, that copper will show the E0 value as positive in the series, and then zinc again decreasing. Okay, so this is the trend, and this decreasing value of E0, that means the less negative value of E0 is indicating that uh, there is a decrease in the tendency to form the divalent cations from the metals across the 3D series. Now, reason for the trend is that this general trend towards the less negative E0 values is primarily related to increase in the sum of first and the second ionization enthalpy across the series. Why we are seeing or why we are observing the less negative E0 value across the series? Because the sum of first and the second ionization energy across the series is increasing. Okay. So more energy is required to remove the true electrons. That's why the E0 value will going to be decrease and decrease across the 3D series. Now exceptions or notable points in the E0 values. It is interesting to observe that the E0 value for manganese, nickel, zinc are more negative than expected from the general. Okay, and why is it so? So basically, if you observe the value of the E0 for manganese, nickel, and zinc, they are going to be more negative than if you are expecting from any general trend. So from the expectation, the value is more negative. Why is it so? So explanations for the deviation. So for the manganese, the more negative E0 value is related to the stability of half-filled D subshells. I said this before, that the more negative E0 value is because the half-filled D subshell stability is going to attain by the manganese in the +2 state. That's why it is showing the more negative E0 value. That means it wants to convert to the Mn2 positive and attain the half-filled D subshell. Now for zinc, zinc is having more negative E0 value because after copper, zinc will come. Copper is positive, copper showing positive 0.34 E0, and suddenly a very negative is shown by the zinc, the E0 value. Why? It is related to the stability of completely filled D subshell in the zinc 2 positive, because zinc from the zinc to positive, it wants to convert to zinc 2 positive, because in the zinc 2 positive, it will going to attain the full filled D10 configuration, which provides extra stability to the ion. So that's why it is showing the more negative E0 value. Now for nickel, nickel is having more negative E0 value because it is related to its higher or highest negative enthalpy of hydration among the 3D series elements. So among the 3D series element, nickel is the element which is showing the highest negative enthalpy of hydration value. This means that nickel 2 positive ions are very strongly hydrated in the aqueous solution, which provides the significant energy release. Okay, that means strongly hydrated in the aqueous solution provides the energy that are provides the energy that is going to release. Okay, and that energy is going to be significant in the significant amount. That's why the Ni to Ni2 positive is considerable due to its highest negative enthalpy of hydration. Okay, and that is why it is showing the more negative E0 value. So if you observe in the manganese and the zinc and the nickel, their tendency or they wants to become from M to positive, like Mn to positive, zinc to positive, and nickel to positive, okay, by some reason. And that is why they are showing the more negative value of the E0 of the standard electrode potentials across the 3D series. Magnetic behavior of substance. Now we shift to our next subsection 4.3.9 showing the magnetic properties. When a magnetic field is applied, the substances exhibit two primary types of magnetic behavior. The one is the diamagnetism, where the diamagnetic substances are repelled by the magnetic field. That means they have no unpaired electrons. Okay, so the diamagnetic substance is going to be the one in which there is no unpaired electrons is present. Every electron are paired, and also they are going to be repelled by the applied magnetic field. The second one is paramagnetism. Paramagnetism is having unpaired electron. Okay, they possess unpaired electron, and paramagnetic substance uh, alternatively from the diatom are going to attract by the applied magnetic field. Now there is another type of magnetic behavior, ferromagnetism, which is an extreme form of paramagnetism. Okay, paramagnetism is already attracted by the applied magnetic field. Now extreme form of paramagnetism is ferromagnetism, where the substances are attracted very strongly to the magnetic field. Many transition metal ions are paramagnetic. That means they possess unpaired electrons in them, and this is a key characteristic of these elements. Now, what is the origin of the paramagnetism? So paramagnetism arises due to the presence of unpaired electron in the elements, right? Now, each unpaired electron has a magnetic moment associated with its spin angular momentum and orbital angular momentum. Okay, so every unpaired electron present in an element, has a magnetic moment which is connected to their spin and the orbital angular momentum. Now, calculating the magnetic moment, spin only formula. Let's see. So, for the first series, that is 3D transition metals, the contribution of orbital angular momentum to the magnetic moment is largely quenched and is therefore not significant. Okay, so the orbital angular momentum contribution to magnetic moment is largely quenched, that means effectively suppressed, or you can say negligible, and is therefore not significant. Hence, for these elements, magnetic moment is primarily determined by the number of unpaired electrons. So, only by the unpaired electrons, we are going to determine the magnetic moment for these three transition metals. And it is calculated using the spin only formula. That's why the name has spin only formula, because we are only considering the spin orbital momentum, not the spin angular momentum, not the orbital angular momentum. So the formula is given by mu equals to under root n plus 2 in the Bohr magneton. Bohr magneton is a unit. Mu is for the representation of the magnetic moment. N, n here is representing the number of unpaired electrons the element is having. So where the n is the number of unpaired electrons, the mu is magnetic moment, which is measured in the Bohr magneton's unit. Key value here is that a single unpaired electron has a magnetic moment of 1.73 Bohr magneton. You can use it at various places. That's why it is mentioned as a key value. That if only single unpaired electron is given, that means n is equals to 1. So 1 plus 2 is 3. 3 times 1 is 1. So under root 3, right? So a single unpaired electron has this magnetic moment of 1.73 Bohr magnetons. Now, let's see observed versus the calculated magnetic moments for 3D ions. So, the experimental data for the magnetic moments are typically obtained from the hydrated ions in the solution or in the solid state. So, for the magnetic moment, the experimental data are obtained from either the hydrated solution, hydrated ion in the solution, or solid state ions. So let's see a table where the calculated and the observed magnetic moments are given. So in this table, you can see the ion are represented for the 3D like series and the configuration of their and their unpaired electrons, their magnetic moment calculated and observed. right? So scandium in the 3 positive is showing the 3d0 configuration. That means it is not having any d unpaired electron. So 0 unpaired electron. So the magnetic moment calculated and observed both will going to be 0. Okay. So this experimental data is observed or is obtained through the either hydrated ion in solution or in solid state. Okay. This is mentioned already. Now in the titanium in the +3 oxidation state have 3d1 configuration. That means one electron which is unpaired is present in it. So one unpaired electron uncalculated will be 1.73. We just have mentioned in the key value that if unpaired electron is 1, the magnetic moment will be 1.73. The observed is a little more, 1.75. Similarly, for vanadium 2 plus, chromium 2 plus, manganese 2 plus, zinc 2 plus. Okay. In zinc 2 plus, if you see 3d10 is the configuration. D10 is the stable one in which every electron in its pair, right? No unpaired electron will going to be there. So unpaired electrons will be 0 and calculated and observed value will also be 0, right? Whereas 3d9 will be different in the copper 2 positive where unpaired electron in the 3d9 is 1. Calculated magnetic moment will be 1.73 and the observed will be from 1.8 to 2.2, greater than the calculated one. Now, what is the observation that you can observe from this table? That for most of the ions of first row transition elements, observed magnetic moment, that is this, are very close to the values that are calculated using the spin only formula, confirming that the dominance of spin angular momentum is more. Okay, so the observe and the calculated value, if you observe in every ion in the first row transition, for the first row transition element ions, you observe that there is the value of the observed magnetic moment and the calculated magnetic moment which you have been derived from by using the spin only formula are very close. That means there is a dominance of spin angular momentum because it can calculate at least, or it can calculate very close value to the observed value of the magnetic momentum. Slight deviations in some cases, for example, iron 2 positive calculated is 4.90 and here observed is very very high, 5.3 to 5.5, and cobalt 2 positive also 3.87 to 4.4, very very high. Okay, so e- as I said that this is DNF block, exceptions going to be there. So exceptions are iron 2 positive and copper 2 positive, where slight deviations is seen, which indicates that some residual orbital contribution or other complex interaction. Okay, why this deviation came? Because due to some orbital contribution or maybe some other complex interaction. That's why this deviation from the calculated to the observed values came in some accepted cases. Okay, let's solve an example marked as 4.8, which is covering the NCRT section 4.3.9. The question is that calculate the magnetic moment of a divalent ion in the aqueous solution if its atomic number is 25. So you have given some time or try to solve this. Basically, you have to remember what is the magnetic moment you have been seen, and for a divalent ion, how you can calculate it if the atomic number is given. Okay, let's see. So for this question, the magnetic moment of a divalent ion in an aqueous solution is going to depend on its electronic configuration. That means the unpaired electron that are going to be present. Just you have to find out that, which in turn determine the element's atomic number. Okay. So atomic number is already given, that is 25, which belongs to the manganese atom. This we already know. So electronic configuration of manganese by using this atomic number you can write as argon 3d5 4s. In the outermost orbital we have 5 electrons in the d orbital and 2 electrons in the s orbital. So electronic configuration of a divalent ion, that is Mn2 positive, will be, so 2 electrons it is going to be loose. So it will going to be loose from the s orbital. So the electronic configuration will become argon 3d5 4s 0. If if you represent this in this diagram, you can see 3d5. That means every like space is filled with one unpaired electron and the 4s is empty. Okay, this 4s subshell is empty. Now, if you want to calculate the magnetic moment, you can apply the spin-only formula, spin-only magnetic moment formula, that is mu equals to under root n plus 2 Bohr magneton, where n is representing the number of unpaired electrons. So, unpaired electrons we can see here is 5, right? 5 number of unpaired electron, that is going to be maximum, is present in this. So, we put the n value as 5. So, mu will become under root 5, 5 plus 2. 5 plus 2 is 7. 7 times 5 is 35. So mu will be going to be equals to under root 35 Bohr magneton, which you can write it as 5.92 Bohr magneton. If you solve this under root, how you can solve this? So I want to give you a trick. So basically, you know, under root 36 is 6, right? Because 6 times 6 is 36. Now if you write the under root of 36, you can write it as 6 times 6, right? 1 6 you have to just take out. Under root means if two the same number is multiplying by each other, you can take one like number outside, and that's going to be the value of that under root. So under root 36 is 6. Under root 35 is just 1 unit less from that under root 36, right? So it is going to be kindly close to 5.9 something. So that's why we can write it here. It's just a trick you can use. Otherwise, you have to apply the proper calculations. So mu here is going to be 5.92 Bohr magnetic. Now let's solve the in-text question, which is 4.8, which is covering the NCERT section 4.3.9. The question is that calculate the spin on the magnetic moment of divalent M2 positive ion aqueous ion whose atomic number is 27. So you have to calculate the spin on the magnetic moment of a divalent ion. The atomic number of metal is already given. So you have given some time. Try to solve this. Try to apply the spin only magnetic moment formula. After this time, we will see the answer. Okay, let's see. So for this question, electronic configuration of the metal whose atomic number is 27, which is already given. It could be argon 3d7 4s2. Okay, so in the d orbital 7 electrons, in the s orbital we have 2 electrons. So this can be the arrangement of the electrons as per the given atomic number. Now for the divalent ion, that is M2 positive aqueous ion, that means 2 electron is going to be donated by this metal. 2 electrons will eliminate from the s orbital and the electronic configuration will become 3d7. So magnetic moment of the divalent ion aqueous ion with n is equals to 3. Now d7 means we just have seen d5. 3d5 will going to have 5 unpaired electron. Now if you increase 2 more electron, or if you add 2 more electrons, so that d7 will become, so 2 of the unpaired electron will going to be paired, right? Another 3 will going to be remain unpaired. So the magnetic moment of M2 positive ions whose unpaired electron is going to be 3 is mu equals to under root n plus 2 Bohr magnet, because we apply the spin only magnetic moment formula, where n is we have already know according to the divalent aqueous ion configuration d7. So n is 3. We put n equals to 3. 3 plus 2 times 3. 3 plus 2 is 5. 5 times 3 is 15. So it will be under root 15. So mu is equals to under root 15, or you can write it as mu is equals to 3.87 Bohr magneton. This also you can find out if I help you, that we know under root 16 is 4, right? 4 times 4 is 16. So one of the 4 you have to take out from the under root 16. So the under root 15 is only 1 less than under root 16. So it is kind of close to 4 value. So it's going to be 3.8 or 3.9. Okay. So mu is going to be 3.87 4 magnesium. Okay, let's move to our next subsection 4.3.10, that is formation of colored ions. The origin of color in the transition metal compounds. DD transition, one of the factor that the color that is observed in the transition metal compounds, especially in the ions with partially filled d orbitals, arises from the DD transition. So due to the DD transitions and in the transition metal compounds, ions will be having partially filled d orbitals, right? Due to which the DD transition happen and due to which the color is going to be present in the transition metal compound. So this occurs when the electron from a lower energy d orbital gets excited to the higher energy d orbital. Okay, when this transition happen between the different energy level of values, okay, of different values. So basically, when an electron move from lower energy level to the higher energy level d orbital, okay, excited, or you can say lower energy d orbital excited to the higher energy d orbital, then this color is going to be observed due to that DD transition. Energy which is going to require for this excitation from lower energy to higher energy corresponds to a particular frequency of light that is going to observe. Okay, because whatever the energy is exciting in this process, that is corresponding to the light frequency, a particular light frequency. Now, this absorbed frequency generally lies in the visible region of the electromagnetic spectrum. Now, electromagnetic spectrum you have covered in the very, very starting of the chemistry level, right? So from there are many regions available or present in the electromagnetic spectrum, one of which is visible region where the you can see the variable colors from your visible, like from your naked eyes. That's why we say that region as visible region. Okay, so the energy that is going to require to excite the lower to excite the electron from lower energy d orbital to higher energy d orbital, that energy is going to correspond to a particular frequency of light absorbed. Okay, that frequency of the light which is absorbed generally lies in the visible region of electromagnetic spectrum. And complementary colors also, the DD transition happens due to which the color is observed in the transition metal compounds. The second factor is the complementary colors. So the color that we observe in the complementary color of the light that was observed, so color that we observed is the complementary color of the light that was absorbed. Okay, so the light color that was absorbed and the color that we are absorbing, okay, that we are observing, are complementary to each other. Okay, so when the electron is exciting from the lower energy level to the higher energy level, and the energy which it is exciting, okay, that is going to be corresponding to a particular frequency of light that is absorbed. Now this absorbed frequency lies in the visible region, right, which is correspond to a particular color. Now the color that we are observing is complementary to the color that was absorbed during this excitation of electron. That's what we are saying. So example is included here that if a substance is absorbing blue light, it will appear yellow because yellow is the complementary color of the blue color. Third factor is the influence of ligand, that is the nature of the ligand. Okay, the ion or the molecule, ligand means the ions or the molecule that is bonded to the central metal ion, which is going to play the nature of it going to play a crucial role in determining the frequency of the light that is going to be absorbed. Okay, so different ligands cause different splitting of d orbital depend upon their energy and their effectiveness. Okay, so different ligands cause the different splitting of d orbitals, leading to different absorption of the frequencies and consequently different obstacle, because if frequency change, the color will automatically change, right? So the color of the absorbed light or absorbed frequency is also going to depend upon the nature of the ligand. Ligand means the atom, the molecule or the ion, an ion which are going to be bonded to the central metal ion in the complex compound. Okay, so these are the factors which are going to affect the or which are like going to determine the origin of color in the transition metal compound. Next is colors of equated first row transition metal ions. We will see this in the figure 4.5. So in the aqueous solutions, water molecule will act as ligand, right? Because water molecule is going to surround the central metal and it is going to act as ligand and going to bonded with the central atom, forming the equated ions. So that's why we are saying equated ions. So there is a table given showing the colors of some of the first row equated transition metal ions. The table is this where configuration, example, and the color are given. So if you see the configuration, if any metal is having or if any ion is having 3d0 configuration, for example, in the case of scandium 3+, then the unpaired electron will going to be 0, right? So the color shown by them is colorless. If there is no unpaired electron, if there is no d electron, basically, if there is no electron present in the d orbital, then dd transition will not happen. There are not the availability of electrons which is going to be like excite from lower energy to higher energy, right? No presence of electron. So if no presence of electron in the d orbital, that means the color will be colorless. Similarly, in the titanium 4 positive, where also in the d orbital there is no electrons, so the color will be colorless. But here d1 is the configuration which is present in titanium in 3 positive oxidation state, then the color corresponding to it is purple color. And if the similarly in the vanadium in +4 oxidation state where one electron is present in the d orbital, the color will correspond to the blue color. Okay, so this is the whole table you can see. And d10 you can see here for the zinc 2 positive. Zinc 2 positive has d10 configuration. That means all the electrons are paired and the d10 configuration is a very stable fulfilled configuration for the zinc 2 positive. So it is also going to show colorless compound because there is no not any excitation of the electrons from lower to higher energy level will happen here in this case. Other than that, in every ion or transition metal, first row transition metal ion in the equated form, you can see they are showing various colors. The key observation from this table are that the ions with completely filled d orbital completely empty d orbital like 3d0 or a completely filled d orbital like 3d10 in the case of zinc 2 positive and scandium 3 positive and titanium 4 positive, they are forming colorless compounds. This is because they do not have any unpaired electrons in the d0 case in the d orbitals to undergo the dd transitions, and also in the d10 case they don't have any unpaired electrons, right? So no empty d orbital available within the same energy level for any excitation. So ions with partially filled d orbital typically exhibit color. The specific color which is depending upon the number of d electrons and the nature of the surrounding ligands. In this case, water, because here the ligand is water. Okay, so the number of d electrons present in an element or present in an ion and the nature of the surrounding ligands is determining the specific color of the ion shown by the ions, right, in this table. Okay, so visual representation. So if you see this figure 4.5, which is showing the colors of some of first row transition metal ions in the aqueous solution. From left to right, vanadium 4+, 3+, manganese 2+, iron 3+, cobalt 2+, nickel 2+, and copper 2+. In these beakers on these containers, you can see that these ions are showing variable colors and these ions are from the first row transition metal, right? The provided image visually demonstrates the diverse colors which are exhibited by the solutions of various d block elements, which is highlighting the phenomenon of dd transitions in them. Now let's move to our next subsection 4.3.11, that is formation of complex compounds. So complex compounds, you can define them as that complex compounds are specialized chemical species where the metal ion, which is known as the central metal ion, bind to number of anions or neutral molecules which are called as ligands. So these bonds form distinct complex species that exhibit their own unique and characteristic properties. Example of complex ions are FeCN whole 6 whole 3 negative, which is hexacyanoferrate in the +3 oxidation state ion. This is a complex compound or complex ion example where iron is the metal ion to which 6 number of cyanide ions or anions as a ligand are bonding. The second example is iron CN whole 6 whole 4 negative where hexacyanoferrate iron in +2 oxidation state ion. Copper NH3 whole 4 whole 2 positive tetraamine copper +2 ion. Okay, so this +3 +2 +2, these are basically the representation for the oxidation states of the central ion or central metal atom. And you also observe that these oxidation state we are showing in the Roman numeral, right? Next example is platinum Cl4 whole 2 negative, that is tetrachloroplatinate +2 ion. So these are the example of complex ions where a central metal atom is present to which the number of anions or neutral atoms are or neutral molecules are bonding. Now, why the transition metals form numerous complex compounds? This is the question that why we observe that transition metals form numerous complex compounds. So transition metals have a remarkable ability to form a large number of complex compounds. This characteristic property in the transition metal is attributed to three main factors if you observe. So the one is comparatively smaller sizes of metal ions. The relative small size of transition metal ions allows them for efficient packing of ligands around the central metal ion, right? So why in the complex compounds, basically the central metal ion is from the transition metals, okay, and relatively it is of smaller size. That's why it can pack itself by a number of ligand around itself, right? So relative small size of transition metal allow it to for the efficient packing of ligands around it, which is like central metal ion, okay, around the central metal ion. Second factor is high ionic charges. So transition metal ions often exhibit high positive charges like +2, +3, and +4. And this high positive charge allow these transition metals to strongly attract and bind with the electron donating ligand. The ligand which are going to donate their electrons because they are already having high positive charges. So they need electrons. So they will attack or they will attract towards the electron donating ligands and bonded with them. Third factor is availability of d orbitals for the bond formation. This is important. The transition metal possesses the vacant or partially filled d orbital. Okay, so transition metals has this property. They have either the vacant d orbital or partially filled d orbital. Partially filled means the d orbital have some number of you can maximally fill the d orbital by the 10 number of electrons. Okay, each subshell can have the two paired electrons in the opposite spin. Okay, so it is possible in the transition metals that the d orbital is partially filled. That means all the boxes are not filled, all the provided boxes for which there are empty spaces which are present in the d orbital, right? That means we are calling them as partially filled d orbitals, due to which and they have also the appropriate energy, right? And due to which this uh, electron donating ligands can you know easily bonded with these transition metal complex ions by donating their electrons, and they have vacant or partially filled d orbitals, they can easily take those donated electrons from the ligands and bond with them. Now these d orbitals can readily accept lone pair of electron from the ligands to form the coordinate or dative bonds, which are the hallmark of complex compound. Okay, this is how complex compound form by the formation of the coordinate bonds between the metal and the ligands. Ligands donate their lone pairs of electrons to the d orbitals of or partially filled d orbitals of metal, due to which the bond will form and the complex compound will form like that. Okay, so let's conclude at the summary. So we covered today the NCRT section 4.3.7 to 4.3.11. First of all, we have seen the halides. So fluorine stabilizes high oxidation states like VF5, chromium F6 due to the higher lattice energy and the bond energy of the fluorine. Low oxidation state of fluorides are unstable. We have seen copper diiodide. So copper CuI2 is unstable. Okay, it oxidizes the I negative, that is iodide to iodine molecule. Copper positive disproportionates and copper 2 positive aqueous ion is stable due to its high hydration enthalpy. Now then we cover the oxides of the transition metals. So oxygen stabilize higher oxidation states up to the group number, right? For example, in the Mn2O7, Mn, that is manganese, existing in the group 7 and existing in the highest possible oxidation state as +7. Also, oxygen is also stabilizing the manganese in its +7 oxidation state and forming the compound Mn2O7. No higher iron oxides than Fe2O3 are observed, because if Fe ferrite will form where Fe is going to be +6, it is going to be unstable and converts to oxygen and this Fe2O3. Oxocations formed stabilize the higher oxidation states, which is outperforming the fluorine. Okay, for example, VO2 positive, where vanadium is in +5, highest oxidation state. Then the reactivity we have talked about. Variable, they show variable reactivity. Most react with acids, and there are also some passive, that is unreactive elements which are present towards the acids like titanium and vanadium. E0 trend we have seen, which decreases across the 3D series. That means it becomes less negative towards across the 3D series due to the increasing of ionization enthalpy, the first and the second one. E0 exceptions we have seen in the case of manganese, zinc, and nickel, which show the more negative value opposite to the trend which was across the 3D series decreasing. But here the manganese, nickel, and zinc show more negative value, which is an exception, which is explained by the electronic configuration stability of manganese and the zinc, because manganese wants to attain its half-filled stable configuration and zinc also wants to attain its full-filled stable configuration. That's why it will show more negative E0 value. Or in the nickel case, the nickel will have high hydration energy. That's why the E0 value is going to be more negative for this. Next, we talked about the magnetism. So diamagnetic, that means no unpaired electron is going to be present. Paramagnetic, unpaired electron is going to be present. Ferromagnetism, which is a form of a strong paramagnetic or strong paramagnetism. What was the origin of magnetism? Unpaired electrons. Okay, and only spin is key for the 3D series. We have only considered the spin only magnetic moment for the 3D series. The formula we have seen is mu equals to under root n plus 2 Bohr magneton. Bohr magneton is the units in which we calculate the magnetic moment, and the n is representing the number of free electrons, unpaired electrons. What was the results? Spin only formula largely matches the observed value for the 3D ions. Okay. So complex compounds. And in the complex compounds, we have seen that metal ions bind to some anions or molecules or neutral molecules, forming unique species known as complex compounds. For example, FeCN whole 6 whole 3 negative, where Fe is central atom, CN is the anion to which It's in six amount. Okay, six number of anions are directly bonded with the central atom, and this is the complex compound. Now, why transition metal form many complex compound? The answer is small ionic size of the transition metals, their high ionic charges, that is +2 +3, they show high positive charge. They have the availability of d orbitals for their coordinate bonding. Now we see the color origin, that is DD transition, where the electrons absorb the visible light to jump between the lower energy to higher energy d orbitals. Then observed color was complementary to the absorbed color by the frequency of the light. Ligand effect, we have seen that ligand also going to affect the color shown by the transition element compound. So ligand split the d orbital into the energy levels, and this splitting will determine the absorbed light frequency and the observed color in the compound. Aqueous ion colors. So colorless, that means uh, the color of the compound in the aqueous form, like color of the ions in the aqueous form was colorless. When when the D is in the 0 configuration, D is in the 10 configuration, D0 in the scandium 3 positive and also in the titanium 4 positive, D10 in the zinc 2 positive ions, where no DD transition is possible because no unpaired electron is present in them. Colored ion, aqueous ion, that means ions with partially filled d orbitals. So there is space provided, or orbital energy level is provided for the upcoming electrons of the ligand lone pairs, right? For the like strong bonding and for the formation of the colored ions. Here the ligand was the water because we are talking about aqueous ions. Example was titanium 3 plus showing the purple color and copper 2 plus showing the blue color. Okay, so thank you so much. That's all for today's chemistry session. Thank you.